this third lecture on the theory of small oscillation. Today we shall start our formulation of the problem using Lagrangian mechanics. Let me first clarify what is our system and what we want to do. Our system, we consider a system comprising of few coupled oscillators. So the oscillators that we are considering are not independent of each other. They are coupled oscillators, means the motion of one is governed by the behavior of one or more of members of the system. As for example, we have considered a linear triatomic molecule or the two masses connected by three springs. These are the system's coupled oscillator because the movement of one is governed by the other all. So we have such a system of coupled oscillator, and the total degree of freedom of the system is n. Small n is the number of degrees of freedom of the system. The system as a whole oscillates about its equilibrium configuration, stable equilibrium configuration. Firstly, let me say what is an equilibrium. Let me remind you what is an equilibrium condition and what is a stable equilibrium condition. A equilibrium configuration is one in which no force acts on the system, and this is valid for each of the degree of freedom. And for stable equilibrium condition, the second derivative is positive. Second partial derivatives are positive, and we have analyzed the stability aspects. This is and we shall call. Furthermore, we shall consider that for each of the degree of freedom, the particle moves slightly from the corresponding equilibrium position. Let me first explain what is equilibrium configuration. If we have a system with 1 degree of freedom, then we generally denote the position by x and the equilibrium position as x0. So the departure from the equilibrium curve position is denoted by x minus x0. If we have more than 1 degrees of freedom, then the equilibrium configuration will be x10, x20, x30. So this is a point in the configuration space. So the corresponding equilibrium position is called equilibrium configuration. So we have a system of n degrees of freedom, and we want to study its behavior around the stable equilibrium position. That is what happens if the system as a whole be displaced slightly from its equilibrium configuration. What will be the effect? Since we are considering motion with small amplitude, that is the heading small oscillation. So we shall see that it is sufficient to keep up to quadratic terms in potential, and that allows a linear force for acting on the system. So this is a linear approximation or small oscillation approximation. So let us start first with the potential energy. So we consider a system of coupled oscillators having n degree of freedom. The equilibrium configuration is so the generalized coordinates are q1, q2 up to qn, and we generally represent it as q, or sometimes we represent it as the set of qi where I is equal to 1 to n. This is a vector and n-dimensional configuration space. equilibrium configuration. Is denoted by Q10, Q20, right up to Qn0. This is Q or a set Qi0. We may use this synonymously, whichever will be helpful in explaining the matter under consideration. And the potential energy of it. Then the force, the generalized force acting on the system is given by Qi is equal to minus del V del Qi. We have assumed the system to be conservative. And in equilibrium configuration, this is Qi0 is del V del Qi evaluated at Q is equal to Q0 is 0 for all I. This is the definition of equilibrium configuration. And for stable equilibrium configuration, we know the second derivatives are positive. So what we do, we introduce a coordinate, modified generalized coordinates. Which is appropriate for this case. This is Qi eta I is equal to Qi minus Qi0. So eta I represents the generalized coordinates which denotes the displacement of the system from the corresponding equilibrium situation. So our first aim is to expand the potential function potential function. We have V as a function of Q. We expand it in Taylor series about the equilibrium configuration so that we write it as V of Q0 plus summation over I is equal to 1 to n degrees of freedom del V del Qi evaluated at Q0 times Qi minus Qi0 plus the second derivative terms I and j runs from 1 to n del to V del Qi del Qj Qi minus Qi0 Qj minus Qj0 plus higher order terms. This we write as the V0, the potential in the equilibrium configuration. This is 0 and equilibrium configuration by the definition. So we have my half summation over I and j. We write it Vij. This is eta I and eta j. Eta I, eta j plus higher order terms. Where Vij is del 2V del Qi del Qj evaluated at Q is equal to Q0 equilibrium configuration, and this is greater than 0 as Q0 is stable equilibrium position, stable equilibrium configuration. As Q0 is a stable equilibrium configuration, so this Vij is positive. Furthermore, we may assume that this here I and j both runs from 1 to n. So we may assume Vij to be the elements or elements of a matrix V, the potential matrix. We may define the potential matrix V is equal to V11, V12, V1n, V21, V22, V2m, Vn1, Vn2, Vnn. You see one thing. Vij, these are the real quantities because it is the potential and we have differentiated it with respect to the generalized coordinates. So, with Vij is equal to real and this is equal to Vji. So the matrix V is a real symmetric matrix. So it is Hermitian matrix. Hermitian matrix. It is a square matrix. It is a real symmetric matrix. Being real symmetric. So the potential energy is a real symmetric matrix, and since we have retained up to second order term, the force that we are going to get from it is a linear function of the generalized coordinates. That is the linearization of the problem. That is, if we could retain still higher order term, then we will have quadratic term in the potential, in the force, and then the corresponding problem will be a non-linear force. But here we retain ourselves with the linearization approximation. And furthermore, this is the we may, without any loss of generality, set V0 to be 0, which is the potential at the equilibrium configuration. So in general, we can write the potential as simply comprising of this. So under linear approximation, under linear approximation we write V as, we write it as half summation over I and j running from 1 to n Vij eta j. So this is the linearization of the potential of the force. So we have found out the form of the potential energy. As I have stated that we shall be adopting the Lagrangian formalism for the solution of the problem. So we need to calculate the potential kinetic energy also. So coming to the kinetic energy, the kinetic energy of a system comprising of capital number of particles can be represented as like this. Kinetic energy T for a system of K is equal to 1 mk rk dot square, k is equal to 1 to n. This is number of particles, or here the number of oscillators of the system, but not the degree of freedom. Now, in general, Ri can be written as Ri of a position of Q and T which I is a function of generalized coordinates qi and of t. So ri dot is summation over j del ri del qj dot. J is equal to, this j is from 1 to n. Small n is the number of degree of freedom, and plus a term that is del ri del d. We assume that the transformation relation is such that this term is not there. So this is our assumption. This is the assumption, and which is found to be valid for for most of the system under consideration. So we can write this part as we have shown this in connection with the Lagrangian and Hamiltonian mechanics, that this can be written as summation over I and j running from 1 to small n. Then we have a summation over k. This is qi dot, qj dot. Then we have summation over k is equal to 1 to n mk del rk del qi dot del rk del qj. In one of my earlier lecture, I might have missed this part mk. So this is written as half summation over ij mij qi dot qj dot, where mij is defined as summation over k is equal to 1 to capital N mk del rk del qi dot del rk del qj. So it is a function of q's. Means it is a function of qi's and qj's, and the k dependence is summed over. So we can expand mij also in Taylor series. So we can write mij of q as mij of equilibrium configuration qj dot plus summation over L is equal to 1 to n del mij del ql times ql minus ql0 plus higher order terms. Here we assume that these parts are negligible, and so that we can approximate it to be mij of qz, in which case this we write it as Tij. Note that Tij depends only on equilibrium configuration, so we write it as half summation over ij Tij, and we have defined furthermore that eta I is equal to qi minus qi0, so eta I dot is equal to simply qi dot, because this is constant, so it can be written as eta I dot eta j dot. So this is the kinetic energy term. Again, Tij may be assumed to be the components of a matrix which is a real symmetric matrix, real symmetric square matrix. So it is again a Hermitian matrix. So the T matrix is like this. We may write T matrix as like B matrix. It is T11, T12, T1n, T21, T22, T2n, Tn1, Tn2, Tnn. So it is a real, symmetric and square matrix. That is Hermitian. So we have written the kinetic energy and potential energy as its components, so we can now define the Lagrangian. Recall that one thing, that we have expanded Mij about the stable equilibrium position, and the value of Mij at the equilibrium configuration has been written as Tij. So the task that we have worked out till now is that the potential energy can be written as half summation over Ij running from 1 to n, Bij eta I eta j, and similarly T is written as half summation over Ij, Tij eta I dot eta j dot. Let me first write explicitly what do we mean by this for a system having 2 degrees of freedom, and then I shall extend it to 3 degrees of freedom. So for n is equal, what is the explicit form? For n is equal to 2, we write V is equal to half, then summation over Ij is equal to 1 to 2, Vij, this becomes half V11, V12, then V21, then V22. So this can be written as half V11 plus half V22 plus V12, as V12 is equal to V21. For any equal to, similar expression can be written for, sorry, I have missed eta I, eta j part. So this is half V11 eta 1 square plus V12 eta 1 eta 2 plus V21 eta 2 eta 1 V22 eta 2 square, which can be written as half V11 eta 1 square plus half V22 eta 2 square plus V21 eta 1 eta 2, as V12 is equal to V21. Now if we want to find out the force corresponding to component 1, so Qy, what is the Qy? Force Qy is Q1, sorry, Q1 is equal to del V minus del V del eta 1. In that case, it is, from it we have V11 eta 1, and from this term we get V12 eta 2. Similarly, the force Q2 is equal to minus del V del eta 2 is equal to, from this we get V to 2 eta 2, and from this V1 to eta 1. So we get the expression. These forces are linear force. This is the linearized force. The forces are linear. Now coming to for system with 3 degrees of freedom. For n is equal to 3, this expression looks like V is equal to half V11 eta 1 square, V half V22 eta 2 square plus half V33 eta 3 square. Then coming to cos term, V12 eta 1 eta 2, V23 eta 2 eta 3 plus V31 eta 1 eta 3. This is the potential, and we can calculate likewise the force. Q1 is equal to minus del V del eta 1. It is a convolution V11 eta 1. Then convolution comes from here. This is V12 eta 2, and then comes from this one V13 eta 3. So we can write the force Q. This can be written as summation over I is equal to 1 to n Q1 in, for Q1 we write P1I eta R. So this is the force acting on the particle. Similarly, we can apply this for degrees of freedom 2 and 3. So in general, we can write Qj is equal to del V del eta j is equal to summation over I is equal to 1 to n Vji eta I. It is immaterial which one or which suffix we write earlier. So this can also be written as V sum over I Vij eta I. So the forces are linearized from, so force is the linear function of the generalized coordinates. Similar expression also holds for the kinetic energy. So the kinetic energy only change will be V's will be replaced by the T's and eta will be replaced by eta dots. So that for this the kinetic energy expression for kinetic energy becomes T is equal to, from this expression, half T11 eta 1 dot square plus half T22 eta 2 dot square plus T12 eta 1 dot eta 2 dot. And for n is equal to 3, for n is equal to 3, we have T is equal to half T11 eta 1 dot square plus half T22 eta 2 dot square plus half T33 eta 3 dot square plus no more halves T12 eta 1 dot eta 2 dot plus T23 eta 2 dot eta 3 dot plus T31 eta 3 dot eta 1 dot. This is the kinetic energy. And if we differentiate with respect to dots, then what we will get? del t del eta I dot eta 1 dot. Then this is here from t11 eta 1 dot eta 1 dot from here. From there we will get t1 to eta 2 dot, and from here we get t13 eta 3 dot. So obviously the Lagrange's equation also lead to a coupled differential equation, as we shall see right now. So Lagrangian form, we shall apply Lagrangian formulation. So the Lagrangian of the system is L, which is a function of Q dots and of T is equal to T minus V. Here we have written T and V in their matrix form, so we write it half summation over Ij is equal to 1 to n Tij eta I dot eta j dot minus Vij eta I eta j. We recall that if we could write the Lagrange's equation, then we need to differentiate it with respect to generalized velocities and generalized coordinates. So differentiation del L del eta k. So this part is no more undergoing differentiation, because Tij are the quantities referring to the stable equilibrium position. So these are constant for a given system. So this part is not acted upon by differentiation with respect to eta k. So differentiation goes over here. So we have minus half summation over Ij is equal to 1 to n. Then we have Vij. Then the differentiation is over this. So this is del eta k operating on eta I, eta j. So this is minus half summation over Ij is equal to 1 to n Vij. Then what we have? This is eta I del eta j del eta k plus eta j del eta I del eta k. Now, since the generalized coordinates are independent of each other, this part leads to a delta function delta of jk, and this also gives a delta function delta of ik. This delta function should have been written in correct tensor notation as delta of kj, because differentiation with respect to the covariant quantity in the denominator, so it will come to the contravariant index, and this will as well will be delta of ki. But still, as we are not concerned with the tensorial notation, we should still use this type of notation. Otherwise, if we could maintain the tensorial character, then this term would have been written in a different way. So, in tensor notation, in correct tensor notation, we should have either written V as half summation over Ij, Vij, since it is a scalar, then it should be written as eta I, eta j, or it should be written as summation over Ij, Vij, eta I, eta j. But we are not going to use this tensorial concept, which is not related required over here. So we use the notation that we are used to use in non-relativistic mechanics, where we do not make use of tensions. Coming back to the expression, this is minus half summation over ij, bij. Then we have from this eta I delta of jk plus eta j delta of ik. When we, for this term, when we sum over j, so let me first write this like this. Ij is over 1 to n delta of jk for the first term minus half summation over ij bij eta j delta of ik. Now for the first term, when we execute j sum, then execute j sum, then only when j is equal to k, this term will contribute. So we have minus summation over I, no more j sum is there. So minus half summation over I is equal to 1 to n pik eta I. And for next term, when we execute the sum over I, then the only contribution comes from I is equal to k. So we write it bkj eta j. There are two sums. These are the dummy sums. I sums are dummy. So we can replace this by a single sum where this half will go. So we write it as bik eta I is equal to 1 to n. Similarly, if we go to differentiate it del L del eta k dot, this will be minus half summation over ij pij del eta k dot eta I dot eta j dot. The general Lagrangian formalism, the Q1 dot and Q2 dot are also independent of each other. So this, following this perception, comes out to be, there is no half, so a minus sign. So this will come out to be summation over I is equal to 1 to n t I k eta I dot. So this is the Lagrangian, and we got the final result for this. So this is minus summation over I is equal to 1 to n v I k or ki, whichever we write, vi eta I dot, and for dots we write del L del eta k dot, we write it as plus summation over I is equal to 1 to n pik eta I dot. So these are the ingredients required for Euler-Lagrange equation to be fed in. So coming to the Euler-Lagrange equation for conservative system. Equation for conservative system. one Lagrangian equation for a conservative system is ddt of del L del Q K dot minus del L del Q K is equal to 0. And we have the component, these things, this Tij are constant, so we get summation over I is equal to 1 to n. From this part we get T I K eta I double dot, because there will be a differentiation with respect to time. So this, and this part there is a minus sign and there is a minus sign which makes it plus. So it is V I K eta I is equal to 0. If we rewrite this subscript suitably, which can equivalently be written as, this is the equivalent of writing it as I j is equal to 1 to n Tij eta j dot, sorry, eta j double dot, this is double dot, plus V I j eta j is equal to 0. There are incoupled equations, and in this notation I runs from 1 to n. So for I is equal to 1, for I is equal to n, what is the form of the equation? Let me write it over here. If we write this equation explicitly, if we write it explicitly for I is equal to 1, then the relation is T11 eta 1 double dot plus V11 eta 1 plus T12 eta 2 double dot plus V12 eta 2, and so on. Ultimately we get T1 and eta n double dot, this is n, not eta, plus V1 n eta n is equal to 0. This is for I is equal to 1. For I is equal to 2, we will have another equation. So there are n such equations. There are n such equations, one each for I in the range less than n, less than 1. So what we do? We get a set in linear equations. We get n numbers of coupled differential equations. Our aim is to solve this set of equations, which will be taken up in the next class. And before leaving, so our task will be to solve such set of equations, which in a compact form can be written as this. The compact way of writing equations. Firstly, we have written V is equal to half summation over Ij, Vij eta I eta j. Now we have already stated several times that Vij can be looked upon as the matrix element of the Hermitian matrix V, and we define a ket vector. Ket eta is equal to a set of this eta 1, eta 2 up to eta n. So it is a column matrix, n-dimensional column matrix in the column matrix. Then we define the corresponding bar eta. Bar eta is like this, which is eta 1, eta 2 up to eta n. If eta were found to be complex, then there are stars over there. So in this notation, we can write it as half eta p eta. This is the compact way of writing the matrix, the potential energy V. So potential energy is we recall that it is a row vector. So it is an n cross 1 vector. This is an n cross, sorry. This is a row, so this is 1 cross n. This is n cross n, and this is n cross 1. This is scalar. So the resultant is 1 cross 1 scalar. So it is the potential energy. Potential energy, which is a scalar, which has been written in this compact form. Similarly, we can write the T kinetic energy can be written as half eta dot T operator eta dot. So in that spirit, this set of equations can be written as, this set of equation can be written as, which we wrote in the component form as the Euler-Lagrange equation. We have written that it is summation over j is equal to 1 to n Pij eta j double dot plus Pij eta j is equal to 0. This equation can be written as T operator operating on eta double dot gives you P operator operating on eta is equal to 0. This is the compact way of writing the equations. We shall, in the next class, we shall start with eigenlist of this equation and find out the eigenvalue problems.